can put this in my pocket, can't I?
Yeah.
Yeah. All right. Let's begin. So this is a talk about what I've been working on for my master's project. And as it says, integer points on genus zero curves. So this is, we can see this in from a number theoretic point of view. You can sort of look at the simplest kind of Diophantine equations, which are ones that involve only two unknowns, Cx and y. So you're looking at integer solutions to some polynomial equation that has integer coefficients. So it's helpful sometimes, certainly in this case, to look at it, well, to not ignore the fact that you're dealing with sort of an object that has much more underlying structure. If you look at the solutions to this polynomial equation over fields, Q, extensions of Q, the complex numbers, there's a whole lot more geometry that's at play here. And you would hope that some of this geometric wonderfulness that we have when we move up to these bigger fields is going to be helpful in saying things about what the integer points are on these curves, and therefore solving these Diophantine equations. So we're going to see that we can get some qualitative information at the very least out of this. So there are two geometric features that are going to be at play here. These are the things that are going to govern sort of the behavior of integer points in these curves. So the first one is the genus. So what is a genus? So there's one way of thinking about it. So I'll start with both the notions I introduced, talking about what we have for smooth curves, and then I'll patch it up later for curves that aren't. So a smooth curve is one where you can have a well-defined tangent line at every point on this curve. So there's no corners, there's no cusps, there's no self-intersections. So everything we're looking at today, as I said, like in the Diophantine equation context, you have equations that have integer coefficients, but you could just as well consider them to have rational coefficients. So they're all going to be these curves defined over Q. So you can talk about solutions to these equations over any extension of Q, and the complex numbers are certainly one of the richer places you can go when you're talking about solutions. So when you take one of these curves, the equations of these curves, and look at the solutions over the complex numbers, you're going to get some kind of Riemann surface, this topological object. And the classic example being elliptic curves. When you look at the Riemann surface for an elliptic curve, you get this torus. So this donut that has one hole, and that hole tells us the number of holes is basically giving us the genus. So for an elliptic curve, the genus is 1. So if you, in general, look at what you have here, you take your smooth curve, you look at this Riemann surface, and the number of holes in the donut, there might be 0, but some non-negative integer that tells you, that will tell you what the genus is. So it's actually pretty cool already that when you're looking just for integer points in the curves, that moving all the way up to the complex numbers and looking at this geometric thing is going to tell us or govern somehow the behavior of the integer points that live on it. So the other feature are what we call places at infinity. So again, I'll tell you what they are for smooth curves before we do anything else. So for smooth curves, this is just the notion of points at infinity. So for those of you who haven't done any algebraic geometry, this is probably no more helpful to you than places at infinity. But I can give you a vague idea of what's going on here, and this is really all we'll need. So let's just think of curves in the plane for the moment. So algebraic geometers like to call this the affine plane. And it's helpful in algebraic geometry to embed this in a slightly bigger space. So we move from the affine plane to the projective plane. So we're just adding in a whole bunch of new points. And it's helpful as well to take our curve that lives in this affine plane, and when you move to the projective plane, you patch it up by putting some extra points in as well. And all those extra points in the curve you throw in, you call those points at infinity, because you can sort of visualize them as living infinitely far off in the plane in some way. So this is all you need to think about when I say points at infinity. This will be sufficient for our purposes. And like I said, when we deal with non-smooth curves, I'll tell you how to interpret that very shortly. So there's a really big hammer theorem that was proved ages ago, 1929, a result of Siegel. And this is going to tell us, based only on the genus and the number of places at infinity, in almost every case we can say what's going on as far as the integer points are concerned. So we're going to take a curve x, and it's defined over the rationals like everything else I'm going to talk about today. So the equation for the curve is defined over the rational numbers. So first of all, the first case is if the genus is at least 1. Or genus 0, but we say something about the places at infinity. And at least 3. Now in these cases, in some sense, it's sort of boring because what we get is finitely many integer points on our curve. Then there are finitely many. So this was done ages and ages ago. And it deals with almost every case you can think of. There's really only a couple cases left. You need to look at genus 0 curves and ones that have less than 3 places at infinity. So that was the focus of my master's project.
Finally, many doesn't mean you can count them.
No.
So that's an open problem still.
Yeah. Yeah, being able to actually enumerate these integer points, yeah. No one knows.
You found 5. Are there only 5, or is there some?
Or are there more? Yeah. Yeah, this is a drawback to this method.
Don't you also need the curve to be non-singular or anything like that?
No, there's a way of patching this, so I'll explain what's going on. But yeah, this is a drawback to this method. So it tells you qualitative information. You know there's finitely many, you don't know how many, you don't know how to find them. So this is going to come out as well in the result that I dealt with in my master's project. All right. So this is, I think the first time it was set down in the literature was by Joe Silverman only 16 years ago. So a big gap between Siegel and Silverman. But this has apparently been known to experts in the field long before Silverman, but he's just the first time to sort of set it down in an elementary way. So I'll credit him with it. And then I provide a somewhat different proof as well. So we're going to take, again, let x be a curve, defined over Q. With genus 0, and at most 2 places at infinity. So there's going to be 2 types of behaviors that arise here. So this is going to depend on the number and type of places at infinity we have. So if x has 1 of these, or 2 that have a field of definition given by some real quadratic extension of Q. So in these 2 cases, we actually get, well, a dichotomy. So there's either no smooth integer points whatsoever, or else infinitely many of them. So there's this little niggling condition about no smooth integer points floating around here. But it's not, in some sense, if you're looking at qualitative information, it's not a huge obstacle to what we're dealing with, because a curve is only going to have finitely many non-smooth points. So you're only throwing off your count by finitely many of these odd points, and you can locate them by setting a bunch of partial derivatives to 0. And you can, if you're dealing with a curve in the plane anyway, you could have a computer just crank out what the solutions are and check them to see if they're integer points. So this is not a huge hurdle from a lot of different perspectives. The other case is if you have two places at infinity defined over different fields of definition. So if Q is the field of definition, or an imaginary quadratic extension. In this case, we get the same Siegel conclusion, that there are only finitely many integer points. So this is our setup, and it completely depends on this sort of geometric feature being what the places at infinity are in this thing. So I want to give you an idea, just a sketch as to what we do to prove this. So this involves a bunch of algebraic geometry, and I don't really want to concern ourselves with the details of this. But it should be nice to give an idea. So we have our starting curve x. Now, in algebraic geometry, we like smooth curves. So we want to make it smooth somehow. And there's this process called normalization you can carry out. So I give you, taking a curve x, I can produce a curve x nu. So we've normalized the curve. And what's nice about normalizations of curves is that they're smooth. Every curve has a normalization, and the normalization of the curve is smooth. And furthermore, for curves, they look a whole lot alike. So they have this birational map between them. Now, for those of you not familiar with this notion, the only thing you really need to know is we can throw topology on these curves as we can with any algebraic variety. It's called the Zariski topology. And a birational map can be viewed as an isomorphism between open subsets of these two things. And on curves, the Zariski topology is such that your open sets are really huge. It's basically the cofinite topology that you have here. The open sets are just where you throw away finitely many points. So for all but finitely many points in both these things, you have an isomorphism between them. So it's pretty much preserving the essence of what x is. And the other nice thing is this is a map that's defined over Q, in the sense that if I plug in a rational point on one of these two, I'm going to get a rational point on the other. So this is sort of halfway to what we want, because I want to transfer the behavior of integer points on x to something that's nicer and that I can understand. So I would like, in some way, integer points to be preserved when I pass through this series of maps, and certainly preserving rational points is a good start.
So this new bit, this not like this is not the Jacobian. It's something different.
Yeah, it's not the Jacobian,
No.
because we're not dealing with...
The Jacobian, yeah.
I'm just wondering. I mean,
Okay, well,
what is it? Like,
here's a reality check, right? Like the Jacobian of a genus, say genus 2 curve, is not a curve.
Yeah.
So how could it be birationally equivalent to the Jacobian? Genus 1 it works because the Jacobian
Yeah,
of
Is
genus 1
the curve.
What happens with the Jacobian when we do in the genus 0 case? It's like it's trivial or something, or?
Well, the other thing you want also, like with these Jacobians for Abelian varieties, so to speak, like you want the thing to be smooth. And I'm dealing with arbitrary...
Yeah, sorry for that.
I'm
I'm just curious. What
But yeah, the whole point of this is I want to
normalization
make the
versus
thing
groups.
smooth rather than...
Yeah.
Yeah.
Okay, sorry.
I'm not really concerned with a group structure, for instance.
Sorry for that. I'm just interested in this particular, like, what is normalization, but I guess we'll just talk about it later. So.
Yeah. All right, so we have this smooth thing now. We have x nu. And there's a whole lot more things I can deduce with smooth curves than I could for the arbitrary curves. So given the normalization of the curve now, the next step is to produce this isomorphism to a conic. A conic living in the plane. And again, this map we produce is defined over Q, so that if I have rational points on one, then I map over to rational points on the other. So we'd like to just pass the question of finding integer points on X to finding integer points in this conic. And it turns out that this, in essence, works. So it's not true that all the points in the conic will translate back, but you can look at the maps you produce and tinker around with things, and once you've looked at it carefully enough, there's sort of in some sense, there's almost a group action you have on points in the conic, and a finite index subgroup of this ends up transferring to integer points on X. All right, so that's all the heavy algebraic geometry I really want to get into. So is there anything I can clarify before I move on to my next topic? All right. So for the rest of the talk, I want to focus on how we solve this case for conics, because you really need to do that before you can do anything else. And this is much more number theoretic in flavor than what I've been talking about so far. I suppose I also promised you what genus and places at infinity are. So that's actually pretty easy. We just pass the buck from X to the normalization. Normalization's smooth, so the genus of X is just the genus of its normalization. And the places at infinity are just the pre-images of points at infinity under this map. So you just pull them back to X nu, and those are your places. All right. So we want to prove a result for conics. And it's just going to directly mirror this, because it really is just a special case of this theorem. With a little terminology transferred over. So we're going to consider a conic in the plane. Similar setup. So what's the story about integer points on conics? So I very deliberately write it to be parallel with our main theorem. So if C is a parabola, or a hyperbola with a non-square discriminant. So if all this terminology I'm throwing at you is unfamiliar, I'm going to give you a lowdown on conics after I'm done here. Then the behavior is we have either no integer points or infinitely many. So the smooth qualifier has now vanished because conics are smooth curves. So you're never going to find non-smooth points. The other case, so if C is a hyperbola with perfect square discriminant, or else an ellipse. Then finitely many integer points, same as case 2 over there. So this is the direct mirror to the theorem you see on this board. The parabola is the case where there is one place at infinity. There's one point at infinity. The hyperbola with non-square discriminant, there are two with fields of definition given by some real quadratic extension, and so on. So the miracle is by solving this case, you actually prove this theorem, basically modulo this messing around with maps. So we want to understand how we prove this thing. So before I go any further, I should tell you or remind you what we're dealing with. What are these conics in the plane? What do their equations look like, and how do we tell them apart? So it has this general degree 2 equation. This might give you a reminder of high school. This is certainly where I saw this the first time, grade 12 math. So this general degree 2 equation. And the fact that it's defined over Q tells me well, that just means I can take these A, B, C, and so on to be rational, but I can then clear their denominators and just assume that they're integers. So A through F, integers. And then I want this to be legitimately degree 2, so one of these degree 2 monomials has to have a non-zero coefficient. All right. And the only other thing I have to throw at this is I don't want it to be a pair of lines. It could be that this factors over the algebraic closure of Q as some pair of lines. And then that's not a conic. That's 2 lines. So we assume that this is irreducible. Over the algebraic closure of Q. So there are 3 types of conics: parabola, hyperbola, and ellipse. And the way you tell them apart is this discriminant I referred to in this theorem. So what is it? It's b squared minus 4ac, which is the same thing you write down when you do a quadratic formula computation. So the sign of the discriminant is actually going to tell us what we need to know. So if d, the discriminant, is positive, the conic is a hyperbola.
So D, E, F actually don't matter?
Not for the discriminant, anyway.
Okay.
Yeah. If d is equal to 0, the curve is a parabola. And therefore, if d is less than 0, we have an ellipse. So because I've rigged it so that all these parameters are integers, we can always take our discriminant to be an integer. And then that's what I mean about whether or not it's a perfect square or not up here in the theorem. So we want to prove this in the 25 minutes or so remaining. Well, the first one's going to be really easy. So we'll knock this off one conic at a time. Now, before I go on, is there anything I can clarify for anyone about the framework here? Is it all making relative sense? All right. So for ellipses, there's basically a 3-word proof, which you can fill in, and one of the words is ellipses, so I'm not really gaining anything. All right, ellipses are compact. Meaning just if you take the real points living on this ellipse, it's actually a compact subset of the plane. So it's bounded, so if you overlay the integer lattice over top of it, then it's only going to hit that lattice finitely many times. So definitely finitely many integer points.
But don't laugh. I mean, it's not obvious how many points there are.
Yes, it's not obvious how many points there are, but you do know there are finitely many.
It is finitely many. If you could count all of them efficiently, you could solve the Gauss circle problem. Gauss doesn't know how to do it. Nobody knows how to do it since then. So.
Yes.
Yeah.
But if you're only after qualitative information, then this
What
beautiful.
if you pass to, say, Gaussian integers, right? Because then you add this complex
Yeah.
dimension to it, and can it be infinite then?
Well, over the Gaussians, if you look at the unit circle, for instance, yeah, I don't know right off the top of my head. You sort of lose this compactness for sure.
Yeah, okay.
But,
that's the thing. So I mean, once you add complex numbers, you lose compactness. So maybe in this case it's more interesting. Okay. So.
Yeah. All right. So parabolae, the fancy Greek plural of parabola. So this one, well, if you look at it the right way, it's not too much harder than ellipses. It's certainly not a 3-word proof. But the trick is we're going to solve a special case first. So we'll look at the ones that look like this. So just say that B and C are 0. And then to make sure this is an honest-to-goodness parabola, we need A naught 0 for it to be degree 2, and E naught 0 because otherwise I can factor it. All right. So this, suppose I have an integer point. I'm going to do this thing where I just reduce mod E. So that's got to be 0 mod E. So in particular, if this quadratic congruence mod E has no solutions, then there can't be an integer point on my curve. So that's sort of half of what I promised. There's either got to be no integer points or infinitely many. So the converse is true as well. So if this has a solution, then in fact I get infinitely many integer points. So if this is true, for some x naught, well, then I can add any multiple of e to x naught and get a solution to this congruence. xk is just x naught plus k times e. And now, we'll just say what this says. So that just means this thing's a multiple of e. I'm just going to name it cleverly. There's a So there exists an integer y naught such that ax naught squared plus dx, actually yk in fact, for any k, plus f is equal to minus yk times e. I can name my multiple whatever I want. So that's just saying now that there's an integer point xk, yk on my curve. And all those x coordinates are different, so I have infinitely many different points. So that special case was actually pretty easy to dispense with. So with that out of the way, it'd be nice to leave this on the board, but I only have one board. Well.
Why did you choose this room?
Why did I, oh, this room?
Because the other room's not available. And do not ever fight with the secretary about room booking because they work really hard to get you a room.
Yeah.
So if
It's
you,
not that bad. It's the board small, right?
Yeah.
and you're not going to have a good time if the secretaries hate you.
You all have comfy chairs, at least. Okay, so we've got the special case done. So it turns out the general case is not too much further away than the special case. Yeah, roughly speaking. So in general, actually, I'm going to hit it with a linear change of variables defined over the integers. So basically, you can give me a matrix, or I can give you a matrix in SL2Z representing this change of variables. There is an invertible, call it a Z change of variables. So given by just a matrix that has integers in it, and this is determinant 1 or -1, I guess you could use. So that the inverse also has integers in it. And what this does is if I plug in an integer point on one, then I get an integer point on the other, and vice versa. So it's not going to change certainly the count of the number of integer points. So there is one of these change of variables taking the parabola to this one, or one of this form. And there's sort of a good geometric motivation behind it. Now for the sake of time, I'm going to leave that, and if I happen to have time at the end, I'm going to come back to it. But yeah, you want to move the point at infinity. For those of you who know what I'm talking about, you put the point at infinity in the same place as this one, and then it looks like that. That's basically the end of the story. So then you're done, because if we've transformed it to this one, and we know there's either no points or infinitely many on this one, so go back through this change of variables, there's either no points or infinitely many on the other one.
And the important thing is that GL2Z action preserves integer points, unlike the rational map you mentioned before. So it is equivalent. Because if you lose integer points in the process, then you're screwed. Right?
Yeah. All right. So it's basically the end of the parabola story. So the hyperbolas are really where the interesting action is happening. So buried in this is the theory of Pell equations, because you write down your favorite Pell equation, it's a hyperbola in the plane. So this should hopefully feature somewhere in our description of the solutions to this thing. So I'm just going to write my general equation slightly differently. So first of all, I almost call it a disclaimer. We can assume that with the same notation as I've been using all along, a is not 0. The coefficient of x squared is not 0. So we can always fix it if it's not. For instance, if the coefficient of x squared was 0 and the coefficient of y squared wasn't, I just swap x and y. And if both the coefficients of x squared and y squared were 0, there's another one, which is harder to say in words, so I won't, but it's pretty easy as well. Then you can just arrange that the coefficient of x squared is not 0. So I'm going to do that, and now I'm going to rewrite this equation, the general conic equation, such that it's basically a quadratic equation in x with coefficients that are polynomials in y. So I'll just write it like this. by plus dx and at the moment it's just a fancy rewriting of things. But it does give us that whenever xy is an integer point in this curve, the quadratic formula tells us there's a relationship between x and y. And this is actually going to be surprisingly helpful. So if I'm going to have a point xy that's an integer point on the curve, then whatever I just wrote down here has to be an integer. And this is an integer. So in particular, the thing under the square root is the square of an integer. For some integer z. The other thing I'm going to need is that my numerator has to be divisible by 2a. Now because of this plus minus flippy, I can always choose my z in such a way that if I'm going to have an integer point, I need z to be congruent to by plus d mod 2a. And conversely, if I have a z and a y integer pair that solve this and solve this congruence, then I can give you the x-coordinate via this, where I just replace this with z. And we've recovered an integer point on the hyperbola. So I've just sort of translated the problem. I've traded in this equation for a slightly less general one, but now with an extra congruence condition imposed on it. So now let's just unpack this equation, see what we can say about it. So we can just open the square and bring the 4a, and I'm going to group everything together so that we got constant times y squared plus constant times y plus constant. So this is, I've done this so many times, I just do it from memory now. And you can check me on this. It's pretty easy to check once I've written it down. So this is, by the way, our discriminant hiding in secret. So this is where the dependence of my result on the discriminant is going to come in. Whether or not there's finitely many or infinitely many. This d is going to seal the fate of this hyperbola. And because I don't want to carry around the extra notational baggage, let's call these e and f. So I'll complete the square first, and then we're going to make it look nicer. So let's pull out this d. So I got y squared plus e over d. And let's add e squared over 4d. Squared. There we go. That's a bad too. Whereabouts? Oh yeah, I do this all the time. All right. So this is d times y plus e over 2d squared minus this thing. All right. So I'm going to move this over to that side and switch the sides or whatever. And I'm going to multiply through by 4d squared. Actually, 4d squared. So overtly, 4d squared z squared minus, I'll bring this 4d squared in, so it's 2d on each factor. 2dy plus e squared, and over here, 4d squared f minus de squared. Now this is also 2dz squared. All right, so now I'm going to again hide some notation. So let's just call this alpha, this beta, and this gamma. So now I've got a really simple equation on my hands, at least much simpler than what we started with. And this is a Pell type equation. If gamma were 1, we'd be, or minus 1, we'd be looking at a literal Pell equation. So we've now traded everything in. This is all equivalent. You can trace the steps back. So if we find solutions to this such that alpha is a multiple of 2d by some integer z, beta is a multiple of 2d plus e for some integer y, and z and y are linked by this congruence condition I started with, then we have an integer point. So for every solution of this kind, I have a point on my hyperbola. So this is the one I want to study because we sort of know more about this. So this corresponds to an element of this quadratic order. Well, maybe I'm getting ahead of myself. So we want to know whether D is a perfect square or not. So I'll deal actually with the easy case first. So suppose D is G squared for some integer G. Then I can factor this over the integers. So we're looking at alpha minus G beta times alpha plus G beta equals gamma. Now, one can check via tedious calculation that the fact that this is irreducible tells me gamma is not 0. So now, if I have an integer solution alpha beta, forgetting about all the other things I've thrown at alpha and beta, just the fact that I have an integer solution alpha and beta tells me that these two quantities would have to be factors of gamma if I'm going to have a solution. So we'll need alpha minus G beta to be some gamma 1 and alpha plus G beta some gamma 2 with gamma 1 times gamma 2 equal to gamma. And gamma only has finitely many decompositions as products of two integers like this. So there's only finitely many systems of equations that will yield my integer solutions alpha and beta. And so, well, the determinant of this system is 2g, which is not 0. And therefore, this has a unique solution, whether it's an integer solution or not. So we have finitely many systems that yield one solution each, which may or may not be an integer solution. So we conclude there are finitely many possible alpha, beta, therefore finitely many points on this curve. So that deals with the case where our discriminant is a perfect square. So does anyone want me to repeat anything I just said?
Can you repeat the last step? Gamma 1 times gamma is gamma. How you conclude?
How we conclude from here. So we have finitely many systems of equations. And each system of equation is a unique solution, which may or may not be an integer solution.
Has a unique solution even over C, say?
Yes.
Yeah. So it's either, it contributes either 0 or 1 solution. Yeah.
Yes. And only when we have one solution that also satisfies this plethora of conditions we've thrown at it do we get an integer point here. So some subset of this system will yield integer points on the curve, and no more than that. All right. So the only thing we have left is where this D is not a perfect square.
It also seems that in this case you can actually try to count them at least.
Yeah, you can try, but it also depends on splitting gamma. If gamma is some huge integer, you have sort of a factorization problem.
Right, yes.
So it's not very computationally efficient.
Okay, yeah, but I mean, in the end, you can just try to quantify, or you can estimate how many of them, right? Because you know how
Yeah,
many
yeah.
factorizations are
In
there.
principle, like this is.
Well, it's
Can it be
big O of e to the log gamma over log gamma.
Exactly, yeah. But you know, it's better than nothing.
Yeah. Yeah, this is in some sense more effective than the proof I threw at the ellipse. That's true.
It's true. In that sense, I guess ellipses is worse.
Okay, so now if it's not a perfect square, I'm going to use this real quadratic order thing I was mentioning. So in the other case, we want things in this ring. Find alpha plus beta root D in Z adjoin root D with norm gamma. That's what we're after. So what I want to prove in this case is there's either no points or infinitely many. So the way I'll prove this is I'll start by assuming there is one, and then I'll use it to crank out infinitely many points. So assume x naught, y naught is one of these points. All right, so tracking through all the work I did, this yields an alpha naught beta naught that has norm gamma and satisfies that heap of conditions that I've thrown at it. Well, the pair doesn't have norm gamma, but and the other conditions. All of those. So we know what to do with this in general. If we just want to get more things with norm gamma, well, you find something with norm 1 and you multiply by that over and over again. U plus V root D. I should say not equal to 1. Something non-trivial. And I guess not minus 1.
Right.
Yeah, we're dealing with a quadratic field, so yes. Okay, so then, and we can always do this via continued fractions. That's one of the fundamental things you do when you talk about continued fractions. So we can always crank one of these out when D is not a perfect square. So then this number, alpha k plus beta k root D, which is my starting number, raised to whatever k, for every integer, has norm gamma. So the only hitch in this plan is, well, is alpha k, beta k going to satisfy this heap of conditions that I've thrown at it? So it turns out, well, naively you'd be like, well, what if k was 1? Does it work? And not obviously. But you persevere and say, well, what if k is 2? If you do the computation when k is 2, the new thing satisfies all the conditions.
So k equals 1 is not?
Not obviously, anyway. You stare at this mess and you're like, I don't know. But like when you do the computation with k equals 2, you can actually, everything works out much more obviously, much more nicely. Or preserved, I should say. So I won't go through those computations here because it is just computations. I can show you in my paper if you're curious later. So it works when k is 2, and therefore it works when k is any even number, any even integer.
So for odd integers, you
Yeah, we just don't know. Like it maybe works out, but it's just not obvious in the algebra. But we're guaranteed anyway when k is even.
Oh, I guess so. You're applying recursion, right? So you're
Yeah.
connecting every second one. Okay, very interesting. Then. Okay, cool.
So then you can march out an infinite parade of alpha k, beta k that satisfy all the conditions, and that translates back into infinitely many points in our curve, proving the result we're after.
Yeah, probably the reason why it works for k equals 2, but not necessarily for k equals 1, is you don't know if x squared minus dy squared equals negative 1 has a solution. But x squared minus dy squared equals 1 always has a solution.
Has a solution.
That's probably the reason.
But it also, like, it's sort of, because you want them to look like this. And it's the ability to strip off this e that is actually the problem when you do k equals 1. Like, that's the thing that doesn't seem to work. But when you do k equals 2, it does. So yeah, I think I should stop here. Thank you very much.
Any questions for Nick? Yeah, you have a question, right?
Well, I'm going to ask him afterwards because it's already 5 minutes.
No, that clock is fast.
Oh, okay. I just wanted to ask
Good.
about the process of normalization. Just a quick explanation of what is it, because that's the first time I hear personally about normalization.
Yeah.
But I guess it's pretty
But-
standard.
So you're familiar with a couple things in algebraic geometry? So like the idea is, So you can do this for a lot of different varieties, but for curves okay, so this is the process we look at. So you take the coordinate ring of whatever you're dealing with, and you take the integral closure of this thing in its field of fractions, and I drew the field of fractions. Okay, there we go. So you want to take integral closure of this. I don't even know what the standard notation for that is, but in its field of fractions for whatever irreducible variety you like. And then this coordinate ring embeds into the new integral closure. And the integral closure satisfies all the things that you need for it to correspond to a variety. It's the finitely generated algebra with no nilpotents.
Okay. And can you actually reconstruct it, like nicely? Right, because I mean this is sort of field theory
Yeah,
construction, right? But
it is an
how would you
abstract
pass,
construction.
Right,
So
right. So how would you pass it from this to?
Well, that's a very hard problem. If what you're suggesting works, in so many cases, you would just solve number theory using algebraic geometry. Obviously, that's not doable. Grothendieck tried it, he thought he got it, and he was wrong, so, you know, it's not that obvious, it's not simple.
yeah, yeah, that's the trick. Like actually producing the normalization in any given case is not.
Right. So I guess even though we have this theorem, like constructing
Technically,
embeddings is difficult, right?
Yeah.
Okay.
Technically, the conic is also a normalization of the. If you want something more concrete, even though we don't know how to get to the conic necessarily, but because it's isomorphic to the normalization, so it's also a normalization.
Yeah, and another thing is that another subtle thing is that a lot of techniques don't pass through this map. Like if you want to try to do circle method in one, and then try, okay, well everything works, right? It's the same thing. No, everything falls apart once you push it through. So that's why you have to have good models that may be singular, because that's actually, say circle method actually works there, right? But if you pass it to some bigger thing, because a lot of these embeddings are embedding some humongous space, right? Like if, for example, you could embed into the Grassmania, which has huge dimensions, and now so you know nothing about it.
Yeah. But you can work around not knowing the normalization if you want to just apply my result. So sometimes it's possible to ascertain how many places at infinity the thing has without actually finding what the normalization is. And when you can do this, and there are also ways of finding the genus without finding out what the normalization is. So if you do these things, you can still apply the theorem even if you don't know what the normalization is. Like I do a couple examples in my...
You also have Riemann-Roch in general.
Yeah, Riemann-Roch. Well, that's how you get this crazy map
Yeah.
between x nu and the conic.
Okay, well, Grothendieck didn't solve number theory using algebraic geometry, but he did solve Riemann-Roch using algebraic geometry. That was his big breakthrough result. He just solved Riemann-Roch. Like, that's it, after Grothendieck, Riemann-Roch is done, no more. Yeah, that was pretty amazing. Okay, are there any other questions?
So which part of this is your original work? Like, is it?
Well, everything I just did for the conics, I didn't read anywhere. I just came up with this myself.
Oh,
So-
okay. Yeah, interesting.
And I didn't discover Silverman's paper until after I was pretty much done this. So
Okay.
my argument is totally, except for one case, independent of his. The one case being, I was like, oh, my way didn't work. I'm going to look at Silverman's because now I know Silverman did this. But-
Okay, so here's something that. So actually, I've been working on a lot of
this
similar
as well.
stuff as well. I didn't even know, but I basically proved the same thing. Basically looking at. But I'm interested in orthogonal groups of binary quadratic forms. So you break it down. It's the same parabola, hyperbola, ellipse, and the reasons why things work exactly the ones that you mentioned. And after I did all that work, I looked at a paper at Siegel and I said, oh yeah, by the way, classically we know, and that was from the 1920s.
Yeah.
So Siegel didn't bother writing it down because he thought it was obvious, and so probably somebody in the 18th century or 19th, 18th century did that.
Yeah, like this goes back a long ways, but no one's really written it down because all the experts thought it was obvious.
Yeah.
But it takes some work to actually...
Yeah, it wasn't obvious to me, and it really did matter for what we tried to do. Okay, any other questions? Okay, let's thank Nick again.